Okay, let's do these section 4.1 practice questions first. We have got to determine here the degree, the leading coefficient, the number of turning points, and the end behavior of a couple of polynomial functions. Remember that the degree is the highest exponent on your x terms. Most of the time will be your x terms, although this variable can change depending upon how the polynomial is defined. But highest exponent on your x terms, leading coefficient will be the number, or I suppose it could be a variable as well, in front of the, so this is number in front of highest exponent x term. So the highest exponent x term, find the number in front of that highest exponent x term, and you will have your leading coefficient. So our degree in this first example here is going to be 5. That is the highest exponent on any of our x's. We've got a 5, a 2, a 1, and then do remember there is an unwritten x to the 0. X to the 0 just equals 1. Anything to the 0 power just equals 1. So we just don't write that x to the 0 there because we wouldn't write 2 times 1. We just write 2. So our degree is 5. And then, of course, the leading coefficient, I'll just write LC, is going to be 4, as the 4 is the number, the coefficient of the highest degree x term. In terms of the number of turning points, so you have a maximum number of turning points. We'll start there. So the maximum number of turning points of any polynomial function, the max is your degree minus 1. That is your maximum number of turning points. So in this case, our degree, so max turning, is going to be the degree minus 1, 5 minus 1 in this case, which is 4. That's the maximum number of turning points. In terms of finding the actual number of turning points, I have graphed this function in Desmos, and you can see this function is always increasing. It's increasing. In this area here, it slows down a little bit. This area here slows down a little bit and then increases again, but there are no turning points in this function. I can zoom out a little bit more and see that this function is basically just coming up from negative infinity and just keeps going all the way to positive infinity without turning at all. So in terms of finding the number of turning points, graphing is one way to do that. Factoring can help you find the number of turning points. Of course, this particular polynomial function does not look like it can be all that easily factored without some synthetic division or some intensive work. So we're going to say the maximum number of turning points is 4, and then by graph, we can see that there are no turning points for this function. In terms of the end behavior, remember end behavior has to do with both the leading coefficient and the degree. If your degree is odd, remember you are leaving the graph at opposite ends. One is going to be going down and up, or one is going to be going up and down. If you are even, it's either both up or both down. And whether you are, let me make that go that way, and whether the leading coefficient is positive or negative will determine which of these scenarios we're dealing with. So this one right here is odd and positive leading coefficient. This one right here is odd and negative leading coefficient. This one right here is degree, even and positive leading coefficient, and this is odd and negative leading coefficient. Do remember that one of the best ways to do these questions is to simply write out, to do questions that deal with end behavior, to simply write out the x squared function. That's the simplest even function to deal with, and then one of the simplest odd functions to deal with is the x cubed function. And you can see that in even functions, we've got the two ends of the graph going in the same direction. In odd functions, they're going in opposite directions. And of course, if we flip the leading coefficient from positive to negative, this guy will just go down and this guy will flip up that way. So keeping in mind the x squared and the x cubed function can be a big help in sort of memorizing or at least deriving all of this information that we wrote here. So the end behavior, in this case, the degree is odd. So let's write this over here. We're going to write end behavior. Oops. End behavior. So the degree is odd, and the leading coefficient is positive. So that is exactly the same as the x cubed scenario. The x cubed, the 3 is odd. There is a positive coefficient here, positive 1. So we know that the two ends of the graph are going to leave at opposite ends, one going down, one going up, and the left half will go down and the right half will go up. The way that we write this with the notation that your teacher most likely wants is as x goes off to positive infinity, so that's this half of the graph. As we move to the right along the x-axis towards positive infinity, we can see that y is also going off towards positive infinity. So as x goes up, y goes up. As x goes up, y goes up. And then as x goes off to negative infinity, so now we're talking about going to the left on the graph, we can see that y, the f of x values, the y values are going off to negative infinity. So that is the end behavior for that polynomial function. In the next 4.1 example here, this g of x functions, you got to be careful. Some students automatically assume that the degree is the exponent on the very first x term. And remember, that is not what the degree of a function is. The degree of a function is the highest exponent. No matter where that exponent appears, it is the highest exponent. We could rewrite this polynomial in what is known as standard form, where our exponents are decreasing in size. So this would be the standard form there. And now we can see that, again, our degree here is going to be 4. Degree is 4. That is the highest exponent on our x terms. Our leading coefficient, our LC here, is -7. -7 is the coefficient of that highest term, highest exponent x term. In terms of max turning points, again, max turning, PTS, that's the degree minus 1, which is 3. So at most, this graph will have 3 turning points. Again, I did go ahead and graph this, and we can see from the graph that we just have 1 turning point up here. So the graph is going up, up. The graph is going up, 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 up. We have 1 turning point up here, and the graph is coming down, 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 down. So it looks like the actual number of turning points from the graph, the number of turning points is 1. In terms of end behavior, the last thing we need to do here, so end, let me make a line here, separate that stuff. End behavior. So remember our our degree, let's start there. Our degree is even. So we know we're going to be dealing with something like the x squared situation. That is an even degree function, the quadratic function, and then our leading coefficient here is negative, so we're going to have to flip this upside down, and now we know that both ends of the graph are going to be going in the same direction, and they're both going to be going downward, which means that as x goes off to infinity, so we're talking about going over this way, we can see that y is going down to negative infinity, and as x goes over to negative infinity, so now we're talking about going this way on the x-axis, we again can see that y is going to be going off to negative infinity. So the end behavior can be described like this. In terms of 4.1, this next 4.1 example, we want to write a polynomial function. Write a polynomial function of lowest degree. So polynomial function, lowest degree, and we know the zeros are -2. Multiplicities are given 4, multiplicity given, and 3 multiplicity given. Okay, so what we're going to do first is we're going to write those zeros. X equals -2. Maybe let's just do this mult of 2 just so we don't forget. So that's x equals -2. That's 1, 0. I'm going to write zeros over here. Our zeros are x equals -2. X equals 4. The multiplicity there is 1, so I'm not going to write that. I won't bother with it. And x equals 3. Those are my zeros. Remember that the way that we get from our zeros to our factors which is what we want to do here in order to write this polynomial function, is we simply write an x, a minus, and then the 0, an x, a minus, and then the 0, an x, a minus, and then the 0. So our factors here are x minus negative 2, x minus 4, and x minus 3. And the x minus negative 2, I'm going to go ahead and erase that and just make it x plus 2. There's the factors of the function. If we need to write the polynomial function in standard form, the form that we were talking about up here, this guy up here is standard form, then what we want to do is we want to FOIL all of this out. I'm going to let you do that on your own. Just make sure that when you do this, you are drawing your distribution arrows. So you'll do these two factors first. Once you have a quadratic trinomial from multiplying these two factors, you will then multiply that quadratic trinomial by this third factor, and you will get some cubic polynomial. Just be careful, make sure that you get your signs right, make sure that you don't make any careless mistakes. The next 4.1 example here, find each 0 and its multiplicity. So in the previous example, we were given zeros and we needed to work our way to the factors. On this subsequent example, we need to go from the factors that are given. We're given some factors here, and we need to find the zeros and their multiplicities, and then we also need to describe what is happening on the graph at each 0. So let's start with finding each 0. You've done this many times. This should not be new or surprising to you. The way that we find each 0, there's various ways. In the simplest cases, a lot of times you can just look at what this number is and flip the sign on it, but also remember the zero product property. You can just set each factor, one factor there, one factor there, one factor there, set each factor equal to 0 and solve for x. So for our first factor, that's very easy. We set the factor, which is x, equal to 0, and we solve for x, which we've already done. So there's 1, 0, x equals 0. This next one, if I set x minus 3 equal to 0, I add 3, I get x equals 3. And again, you can arrive at the 0, x equals 3 by simply flipping the sign on that negative 3, flipping the sign on the number here in the factor. So x equals 3 is another 0, and then I'm going to set this last 0 equal to, this last factor equal to 0, and I'm going to solve for x, and I'm going to get negative 2. I'm going to rewrite those over here. X equals 0, x equals 3, x equals negative 2. Those are my zeros. Zeros are x equals 0, x equals 3, x equals negative 2. Don't forget what your zeros are. Your zeros are the x values that will make the function or the y value equal 0. And indeed, if I throw in 0 or 3 or negative 2 in for x, the f of x value will be 0. So those are my zeros. In terms of multiplicity, all of these are a multiplicity of 1. Remember, multiplicity can be determined by the exponent on each factor. So in all these cases, I just have ones, unwritten 1 exponents here. So x to the first, x minus 3 to the first, quantity x plus 2 to the first. So all of these are multiplicity of 1, 1, 1, 1. And then in terms of what is happening on the graph, remember that we determine what's happening on the graph at each 0 from the multiplicity. If you have, so if your multiplicity is even, remember that what happens is the graph at the 0, so let's say this is some 0 value. This is, I don't know, x equals, let's say 3 in this case, or x equals negative 2. This is some 0. If the multiplicity of that factor, if the multiplicity of that 0 is even, the graph will touch at that 0, as opposed to if the multiplicity is odd, the graph will go through at that 0. Okay, so again, this is the x-axis, and where a graph hits, let me clean this up a little bit. There we go. Where the graph hits the x-axis, the x-intercepts, in other words, those are our zeros. Those are the x values that make the y value equal to 0. And depending on whether the multiplicity is even or odd, we know that the graph will either touch and then go back up, in other words, be tangent to the axis, or the graph will come down and go through, or even come up and go through. And also we could have something like that too for the even multiplicity. So all of these are through. They all pass at each of these zeros. The graph will pass through the axis because all of these multiplicities are odd. You can go ahead and graph this function in Desmos, and you will see that at all of these zeros, the graph is cutting right through the x-axis. The next example here, so again, let's set x minus 6 equal to 0 and x plus 4 equal to 0, and let's go ahead and solve for x. So we get x equals 6 minus 4, we get x equals negative 4. So our zeros, of course, are x equals 6 and x equals negative 4. The multiplicities, again, can be determined by the exponents on the factors. So the multiplicity of that x equals 6 is 2. We could also just write 2. And the multiplicity here is 1. Because this is an even multiplicity, we know that this graph will be, let's do this. At x-axis, at this 0, we are touching. Okay, this is the even multiplicity. So in this case, we're just going to be touching. And in this case, we're going to be going through because of the odd multiplicity. So again, at the x equals 6, 0, we are touching. At the x equals negative 4, 0, we are going through the graph at the x-axis at that 0. We need to determine whether x minus 2 is a factor of this polynomial. There are multiple ways that we can do this. I will be honest, I'm not exactly sure which way your teacher wants you to do this because I don't remember specifically what was going on in 4.2, but my guess is we can be using synthetic division here and figuring out whether our remainder is 0. So let's do that. We've got a 3, we've got a negative 6, we've got a negative 5, we've got a 10. We're going to drop the 3. 2 times 3 is 6. Negative 6 plus 6 is 0. 2 times 0 is 0. Negative 5 plus 0 is negative 5. 2 times negative 5 is negative 10. 10 plus negative 10 is 0. So indeed, what this tells us is that the remainder is 0 when 3x to the 4th blah, blah, blah is divided by x minus 2. That's what's going on in synthetic division. This is just a shortcut way of dividing a polynomial of a certain degree by some linear factor. So when we divide 3x to the 4th blah, blah, blah by x minus 2, we're getting a remainder of 0. And when we divide something by something else and get a remainder of 0, we know that the numerator is divisible by the denominator. We can see that with just numbers, like 12 divided by 3 equals 4, remainder 0. That tells us that this denominator goes in evenly to this numerator. In other words, this guy is a factor of this guy. Well, what we just did in synthetic division is we determined that 3x to the 4th blah, blah, blah divided by x minus 2 gives us some quotient. We know the quotient because we have our coefficients of the quotient, but we don't have to worry about that right now. But it gives us some quotient and then the remainder of 0, which means that this denominator is a factor of this numerator in the same way that when we get a 0 up here, we know that that 3 is a factor of 12. The 3 goes in evenly to 12. So remainder is 0 when 3x to the 4th blah, blah, blah is divided by x minus 2. So x minus 2 is a factor of the polynomial. All right, that is 4.2. Next, 4.2. Find the zeros. Find the zeros of this function, and we want to verify using, so verify with synthetic division. So I suppose we just look at the graph here. One of the zeros looks like approximately negative 3. That one over there looks like about negative 3. And this one over here looks like about 4. So from the graph, we can approximate these zeros. So let's go ahead and write down approximation based on the graph will be x equals negative 3 and x equals 4. But the way that we can verify whether these are actually zeros is, again, we can use synthetic division as we're told to do. So what we are going to do is what we just did on the previous question. We are going to, we've got a 3, 2, 1 0 here, so that all looks good. Let me make sure I didn't miss any missing components here. No, got them all. So 1, -5, -8, and 48. Drop the 1, -3 times 1, -3. Add these, -8, this is 24, -8 plus 24 is 16, -3 times 16, -48. We add those together, we get 0. So the remainder when x plus 3 goes into that x cubed function is 0, and that means that x plus 3 is a factor of the x cubed function here, and because x plus 3 is a factor, that means that -3 is a 0. If x plus 3 is a factor, then x equals -3 is a 0. So we have confirmed that that -3 is a 0 of this polynomial function. Let's try the 4. So again, let's try to do this quickly but carefully. So we drop the 1, multiply by 4, add those together, get -1, -4, add those together, get -12, -48, and indeed we have verified that x minus 4 is a factor. That's what this remainder of 0 tells us, that x minus 4 goes into this cubic polynomial evenly. X minus 4 is a factor, which means that x equals 4 is a 0. We have verified both of these zeros using synthetic division. Next, 4.2, solve. Solve by factoring. We need to solve by factoring. So in this first example, we are going to let's just go ahead and do this sort of with the good old trial and error method. We know that we need an x to the 4th. These first two terms have to be x squared and x squared. This 40, I'm going to write my factors 1 and 42 and 24 and 10. It looks like that 4 and 10 are going to be, that's going to be the pair that gives us that -14. Both of those are going to have to be negative to give us the positive 40 and the -14. So it's going to be x squared minus 4, x squared minus 10. Let's FOIL this all back through to make sure we get what we need. So that's x to the 4th minus 10x squared minus 4x squared. So that is the -14x squared. Great. And then the plus 40. So indeed, we do get everything that we need here. Now, of course, on the left over here, we have a difference of squares, which can be factored into x minus 2 and x plus 2 and x squared minus 10. So in terms of solving, we need to actually find the x values that solve these equations. So remember, solve this equation. We need to find the x values that will make this equation true, that will satisfy this equation. So we do what we always do. We set each of these factors equal to 0, because if all three of these multiplied together have to give us 0, then one of these factors would have to be 0. So x minus 2 would have to be equal to 0, or x plus 2 would have to be equal to 0, or x squared minus 10 would have to be equal to 0. Add the 2, we get, I'm going to write these over here, we get x equals 2. Subtract the 2, we get x equals -2. In this case, we're going to add the 10, we get, I'm going to write this here, x squared equals 10. We can square root both sides, but we do have to remember to account for the fact that both a positive root 10 and a negative root 10 when squared will give us 10. In other words, if x squared equals 10, we know that root 10 squared would give us 10, but we also know that negative root 10 squared equals 10, which means that x could also be root 10 or negative root 10. So there's our 4 solutions, our 4 zeros. By the way, something at the top of the page here that we discussed, the fundamental theorem of algebra, remember, says that the degree of a function equals the number of zeros. And interestingly enough, on this example we just did, we can see that we have a 4th degree polynomial here, and we have 1, 2, 3, 4 zeros. I took up a lot of room here, so I am going to rearrange some stuff. I'm going to put this down here, and I'm going to try to move Oh my goodness, that's not what I wanted to do. I'm going to try to move all of this up just a little bit. Let's see if I can do it. Not bad. I moved some of those circles, but that's okay. So I'm just moving that all over. Now in the next example here, solving by factoring, first thing that I can do, I have an x that's common to all three of these terms, so I can pull that x out. I get x times 2x squared minus 4x minus 35 equals 0. Let me just distribute this back through to make sure we get what we had originally. That's x times 2x squared, which is 2x cubed. Yes, that's negative 4x times x. That's negative 4x squared. Good. And then the negative 35 times the x will give us the negative 35x. So everything looks good there. Now, you and I did we did discover that this 2x squared minus 4x minus 35 is not we cannot factor that any further. That's as factored as it can get. So what we would do here is we know that either x or this entire trinomial would have to equal 0 in order to produce a 0 over here. So we know that x could equal 0, or all of this could equal 0. 2x squared minus 4x minus 35 equals 0. And the way that we would solve an unfactorable trinomial quadratic like this is we'd have to use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm going to write my a value, my b value, and my c value. Sorry, that should have been a 35. Didn't mean to confuse anyone there. Minus 35. So my b, that's negative 4 plus or minus square root of b squared. So that's negative 4 squared. Negative 4, that's ugly. Let me not make a careless mistake. Negative 4 squared minus 4 times a times c all over 2a. So let's see here. This is going to be 4 plus or minus the square root of 16 minus, oh man, I'm doing that in my calculator. I'm not gonna do all that in my head. If you don't get to use a calculator here, then you're gonna need to do this in your head. But let's do 4 times 2 times negative 35. So that is going to be negative, all of this is negative 280, but we're subtracting that negative 280, which means we're adding 280 all over 4. So that is 4 plus or minus, what is that? That's 296 all over 4. Getting a little crazy here with room. So that's 4 over 4 plus or minus. What perfect square goes into 296? 296. I don't know how that breaks down. Divided by 36, 296 divided by, how about 4? Does 4 go into that? Yes. So 296 can be written as 4 times 76. So that is 2 root 70, 2 root 76. So 4 over 4 plus or minus 2 root 76 over 4. This is 1. This is plus or minus root 76 over 2. So I'm just canceling there. 2 over 4 is 1/2. So there's my other two roots. My first root was right here, this x equals 0. And my other two roots would be, so I'll write them all up here. X equals 0, x equals 1 plus root 76 over 2, and 1 minus root 76 over 2. So those are my 3 zeros, and indeed, if you have an unfactorable or not nicely factorable trinomial quadratic, it doesn't even need to be a trinomial quadratic, it could be a binomial quadratic. You can use the quadratic formula to find the zeros of any quadratic function. So those are the zeros, and we did solve them by factoring, although in that second case we also had to use the quadratic formula. In terms of 4.3 here, find a polynomial function of degree 4 with zeros 1, negative 2. So we have to find polynomial function, degree 4, with zeros, these guys. And we have to write our answer in standard form. Okay, so again, our first step here is to, let's list the zeros given. We are going to apply the conjugate roots theorem here. We know that if we have an imaginary root of 3i, we must also have an imaginary root of negative 3i. 3i and negative 3i are conjugates of each other. Imaginary roots always occur in conjugates, as do irrational roots. So if they had told us that we had the irrational root 2, we would know that negative root 2 would also be a root or a 0. So here's our 4 zeros. Remember that to get from our zeros to our factors, we simply write an x, a minus, and then the 0, an x, a minus, and then the 0, but I'm going to clean that up and make it x plus 2, and then the x, a minus, and the 0, and an x, a minus negative 3i would be plus 3i. So there's our 4 factors. Now, again, we're just doing some distribution, although over here we should recognize, we recognize that we're dealing with a difference of squares factor. Do not forget to recognize when you're dealing with something like a minus b, a plus b, that is always going to be equivalent to a squared minus b squared, and vice versa. You can go either direction here. You see one thing squared minus another thing squared, you can factor to a minus b, a plus b, and if you see a minus b, a plus b, you can distribute to a squared minus b squared. So in this case, our a is our x, so a squared would be x squared. In this case, our b is 3i, so b squared would be 3i squared, and then there's a minus between them. Remember that 3i squared, don't forget what that means. That means 3i times 3i, which means 3 times 3 times i times i. 3 times 3 times I times I. 3 times 3 is 9. I times I is an I squared. I squared equals, let's write this little side work over here. I squared equals I times I. I times I is root negative 1 times root negative 1. And anytime we multiply two of the same square roots together, all that happens is the root symbol goes away and we're just left with the radicand. So 9 times I squared is 9 times negative 1, which is negative 9. So this all becomes x squared minus negative 9, which is x squared plus 9. And then over here, we still have our other two factors, x minus 1, x plus 2. And then this just becomes a game of distribution where you just have to be really careful and not make any careless mistakes and so on and so forth. It'll take a bunch of steps and some intensive work, but as long as you're careful and as long as you're deliberate and as long as you're, drawing your loops so that you know what you're multiplying at any given time, you should be fine here. So again, you just have to go ahead and distribute all of these and then write your final polynomial, which will be a polynomial of degree 4, because you're multiplying x squared times x, which will give you x cubed times another x, which will give you x to the 4th. In the next 4.3, same sort of thing here. We need polynomial function, degree 3, zeros, negative 3, and root 2. So again, let's write our zeros. Remember, we said that when we have an irrational root, we talked about the fact that an irrational number, in this context, you will be able to spot an irrational number if you see the square root of a non-perfect square. So if you see the square root of a non-perfect square, you know you're dealing with an irrational number. Okay, root 25, that's the square root of a perfect square. That equals 5. That's a rational number. But root 26 is not a perfect square. So this is going to be an irrational number. Okay, so root 2 is not a perfect square. So root 2 is an irrational number. And when we have one root that is an irrational number, we know that we are going to have its conjugate as well as another root, as another 0. So if root 2 is one of our zeros, then negative root 2, not root negative 2. That's not what we're talking about here. We're talking about negative root 2. That will be, that negative root 2 will be another 0. So remember, to go from our zeros to our factors, we do x minus and then the root. But again, let's just clean this up, make this x plus 3, x minus the root, x minus negative 2. So again, that's going to be x plus 2. So there are our factors. In this case, I'll multiply this out for you just so you can see how this goes. So again, we should recognize there's going to be a difference of squares here. Just so we, in case we haven't realized, anytime we're given a irrational root like we are here, or an imaginary root like we were on the previous question, we're going to end up with that situation where we see an opportunity to use our little difference of squares shortcut, because we're always going to have x minus that one imaginary or irrational root and x plus that imaginary or irrational root, which means we're always going to end up in this situation where we're looking at a difference of squares factors. So it's factored. So this will be x squared minus root 2 squared, which is just 2. So x squared minus 2 will be the factor over here. And over here we have the x plus 3. By the way, if you do forget the difference of squares shortcut, that's fine. You can just go ahead and FOIL all this out. X times x is x squared. X times root 2 is plus root 2. I'm going to write the x in front in this case just to make sure my x doesn't get covered under that root. So that's x times root 2, x root 2, and then negative root 2 times x, that will be minus x root 2, and then the negative root 2 times the positive root 2 will be negative 2. Okay, so again, remember, root 2 times root 2 just equals 2. When we multiply the same square root by itself, we just end up with the radicand alone without the root. But here we're doing one negative and one positive, which means we're ending up with negative 2. That's where we're getting that negative 2 on the end there. These two middle terms will cancel out. Positive x root 2 minus x root 2 minus x root 2 is 0, and we end up with x squared minus 2. So don't forget, if you do not see the difference of squares shortcut, that's fine. Not all is lost. You can just go ahead and FOIL the way that you normally would. This last step here, I'm going to let you FOIL this out into the cubic polynomial that you would need here. 4.3, find all zeros of the polynomial given below, verify all zeros. So find all zeros and then verify all zeros using appropriate methods. Again, you need to look back at 4.3 and find out what the appropriate methods are. We could use synthetic division. That's probably what we'll end up doing here. So it looks like our zeros are negative 3 and 1. So let's jot those down as our prospective zeros. So x equals negative 3 and x equals 1. So the way that we could verify this is we could go through synthetic division. You may also have learned that you could plug negative 3 and 1. You definitely have learned this, that you could plug negative 3 and 1 into this function, and if you get out a 0, then you know that these two x values are the x values that produce a f of x or y value of 0, and therefore these guys are zeros. In fact, let's do it that way. This one will be easiest to start with. So when we plug 1 into this polynomial function, we get 1 to the 4th plus 2 times 1 cubed plus 1 squared plus 8 times 1 minus 12. So this is just 1 plus 2 plus 1 plus 8 minus 12. 1 plus 2 is 3, plus 1 is 4, plus 8 is 12, minus 12 is 0. And we just confirmed that this 1 value for x will produce an f of x or y value, an output value of 0, and therefore x equals 1 is indeed a 0 of this function. This 1 is an x value that will produce a y or f of x value of 0, and therefore this 1 is a 0 of the function. With the negative 3, we could actually do the same thing. It's just going to be a little bit more time consuming, and the numbers might get a little bigger here. If you're allowed to use the calculator, this will be no big deal. If you are not, then synthetic division might be the way to go to see if your remainder is 0. But let's see how this works. If I do need my calculator, I might use it. Negative 3 to the 4th, that's going to be 81. 3 to the 4th is 81. This negative will go away because I'm multiplying four negatives by each other. Negative times negative is positive, times another negative is negative, times another negative is positive. So I'm getting 81 there. 3 to the 4th is 81. And then plus 2 times negative 3 cubed, that's going to be negative 27, plus 9 minus 24 minus 12. So what do we get here? This is 81 plus, this will be negative 54, plus 9 minus 24 minus 12. How should we do this? Well, let's just do 81 minus 54. 81 minus 54 is what? 27 plus 9 minus 24 minus 12. 27 plus 9 is 36. Minus 24 minus 12. 36 minus 24 is 12 minus 12. And we have verified again that when negative 3 goes into this function for x in all of these x positions, we do indeed get out a 0. So when x equals negative 3, f of x or y equals 0. So negative 3 is indeed a 0 of this function. Next, okay, so we are graphing this rational function, and we need to graph, and then we need to identify location of asymptotes, a minimum of 4 points. Okay, fine. So parent function here is obviously 1 over x, but we've got some transformations, like an upwards translation here. We're also going to have a left-right translation here. This is a rightward shift of 3 units. This is an upward shift of 2 units. But so again, that's just looking very quickly at the graph and seeing sort of what our parent function is, 1 over x, up to, and we are also going to be going right 3. In terms of the asymptotes, remember that asymptotes are the vertical lines that will occur at any x value where the denominator equals 0. So again, those will be, in this case, our vertical asymptotes. We will have them at any x value that makes the denominator equal 0. So denominator equals 0, solve for x. So we're going to have a vertical asymptote here at x equals 3. X equals 3 is also a prohibited value in the domain. Our domain cannot include x equals 3 because when x equals 3, the denominator will be equal to 0, and this function will be undefined. When a denominator equals 0, we are talking undefined. So there will be a vertical asymptote here at x equals 3. So let's write that down. Let's write VA at x equals 3 because we are told to clearly identify the location of any asymptote. And then in terms of what else we have to do here, let's go ahead. Sorry, they say any asymptote. So why don't we just go ahead and do our horizontal asymptotes as well, which we can do in a number of ways. One of the ways that we can do it is by remembering our horizontal asymptote rules. The horizontal asymptote rules have to do with the degree of the numerator and the degree of the denominator and how the sizes of those degrees compare. So remember, in this case, I'm going to ignore this plus 2 for a moment. In this case, we have a 1x to the 0. That numerator, that 1, that is a constant function. That would be like the function y equals 1. That's just a constant function. The value of this function is always 1, but there is an unwritten x to the 0, x to the 0 being 1. 1 times 1 is 1, but we just don't write that other times 1 there. So the numerator degree is a 0 here. The denominator degree, that is a linear function. There is an unwritten 1 on that x. So our numerator degree is 0. Our denominator degree is 1. So normally we would have a horizontal asymptote at y equals 0, which is the x axis. Okay, so when the numerator degree is less than the denominator degree, numerator degree less than denominator degree, we know that we have a horizontal asymptote at y equals 0. However, this function is not just 1 over x minus 3. This function is 1 over x minus 3 plus 2. So all of the parts of this function would get shifted up by 2. So if our original horizontal asymptote were at y equals 0, the horizontal asymptote here is going to be at y equals 2 because, again, that vertical shift. So there's our horizontal asymptote at y equals 2. And now in terms of graphing, why don't we have to find 4 points. So let's at least do the x-intercept, which we will get by throwing in y equals 0, or in this case, f of x equals 0. So again, to find my x-intercept, I'm going to throw in 0 for y. So that's going to be 0 equals 1 over x minus 3 plus 2. Solving for x here, let me go ahead and subtract 2 from both sides. I get negative 2 over there, 1 over x minus 3. Multiply both sides by x minus 3. Let me put these both in parentheses. So over there on the right, these two guys cancel. I get 1. Negative 2 times x, that's negative 2x. Negative 2 times negative 3, that's plus 6. Minus 6 minus 6. Negative 2x equals negative 5. Divide by negative 2, divide by negative 2. X equals 5 halves. So my x-intercept will occur at 5 halves, comma 0. 5 halves is 2.5. So that is going to be, there is my x-intercept. So let me do this. My x-intercept, the question tells us to identify a minimum of 4 points. So my x-intercept is 2.5 comma 0, or 5 halves comma 0. What about my y-intercept? Y-intercept, remember that happens at x equals 0. So that's 1 over 0 minus 3. I'm just throwing in 0 for my x, plus 2. That's negative 1/3 plus 2. Negative 1/3 plus 2. I'll do this the formal way. Let me find a common denominator over 3. So that's 6 over 3. Negative 1 plus 6 is 5. 5/3. So that's 0 comma 5/3. That will be my y-intercept. 0 and 5/3, that's 1 and 2/3, so that's here, approximately. So my y-intercept is 0 comma 5/3. So I should be able to see now that my graph is gonna do something like this. And I know that mostly from the parent function. I know that because of the asymptotes. And then there should be another leg over here. Parent function of the 1 over x function always looks something like that. So I know there's going to be another leg over here, but since I have to identify a couple more points, why don't I use x equals 4? Oh, goodness. Might need another piece of paper here. I'm going to use x equals 4. Why don't we do a table of values here? Probably should have put some of this work in there. You know what? I'll do that right now. 5 halves, 0. What did we get over here? We got the 0, 5/3. Now I'm throwing in 4. So that's 1. So that is 1 over 4 minus 3 plus 2. Oh, that's easy. 1 over 1 is 1 plus 2. So that's 4 comma 3. And indeed, I've just kind of confirmed that that other leg will be up there. So that's another point. And then how about a fourth point? Why don't we just use 5? How about that? So that's 1 over 5 minus 3 plus 2. That's 1 over 2, which is 1/2, plus 2. That's 2.5. So that is 2.5, or 5 halves. So that's 5 comma 2.5, which is about there. And again, the other leg is going to look something like that. So there are my vertical asymptote, my horizontal asymptote, the 4 points, 1, 2, 3, 4, and my graph nicely sketched here. Next, graphing the function f of x equals 1 over x plus 1 squared minus 2, and we're doing the same thing here. So we're graphing, we're identifying the asymptotes, we're identifying minimum of 4 points. So the asymptotes, let's start there. We know that our vertical, let's start with our vertical asymptotes, okay? So remember, we set the denominator equal to 0. And we solve for x, square rooting both sides. We get x plus 1 equals 0, minus 1 minus 1. We get x equals negative 1. So the vertical asymptote is going to occur at x equals -1. Remember that is a horizontal, sorry, not a horizontal, a vertical line. A vertical line at x equals -1. So there's going to be one vertical asymptote there. Horizontal asymptote, let's use our rules. Again, here we have an x to the 0 in the numerator, and we have an x squared in the denominator. Remember that when we FOIL out x plus 1 squared, it's going to be x plus 1 times x plus 1. And when we FOIL this out, x times x is going to give us x squared. So there is a quadratic down there in the denominator. So that's x to the 0 over x squared. So we've got the same situation here where the numerator degree of 0 is less than the denominator degree of 2, which means normally our horizontal asymptote would occur at y equals 0, which is the x-axis, but everything on this graph is shifted down 2. This is a vertical shift of 2 down. So our horizontal asymptote will not be at y equals 0. It will be at y equals -2, which means we're going to have a horizontal asymptote here. By the way, we should have started off by talking about the fact that the parent function here is 1 over x squared. Remember that 1 over x squared usually looks like this. So what we have here is we just have a leftward shift of 1 and a downward shift of -2. So this is the 1 over x squared parent function, which normally looks like this, but we're going down 2 and we're going left 1, which makes sense. Normally our origin would be here, but we're going left 1 and down 2 to kind of get to our new origin, the new place where the two asymptotes intersect is that -1, -2 point there. So anyway, again, we're assuming that our graph is going to, look something like this. I'm going to erase this in a second, but it's going to look something like this. But let's go ahead and find our 4 points. Maybe we should identify our vertical asymptote at x equals -1 and our horizontal asymptote at y equals -2. So table of values. Let's do a table of values this time. So x and f of x, let's do the intercepts first. So let's say we want to find our y-intercept. We're throwing in x equals 0. So let's do some of this scratch work over here. 1 over 0 plus 1 squared minus 2. That is 1 over 1 squared, which is 1 over 1, which is 1 minus 2, which is -1. So 0, -1. Let me get rid of that origin point there so we don't get confused. So 0, -1 is our y-intercept. What about our x-intercept? Remember, we throw in y equals 0 to find our x-intercept. So that is 0 over x plus 1 squared minus 2. Add the 2, add the 2. We get 2 equals 1 over x plus 1 squared. What do I want to do here? I'm going to multiply both sides by that x plus 1 squared. So times x plus 1 squared times x plus 1 squared. The x plus 1 squared, wow, this is taking up a lot of space here. So x plus 1 squared times 2 equals 1. I'm going to go ahead and divide by 2 to get rid of this 2. So I get x plus 1 squared equals 1/2. And then what I do is, this is going to get a little ugly, but that's okay. I get x plus 1 equals, remember I have to account for the fact that I could get both a positive or negative. I'm square rooting a squared variable expression here, so I have to account for both the plus and minus scenario. Subtract 1, and I get that x could equal -1 plus the square root of 1/2 and -1 minus the square root of 1/2. So again, that did get a little ugly there, but that's okay. -1, so let me do that up here. X could equal -1 plus -1 plus square root of 1/2 and -1 minus the square root of 1/2. Both of those will give us 0. So what is that approximately? That's -1 plus root 1/2. That's a tiny number. So that guy's going to be about there. -1 plus the square root of 1/2, and then that -1 minus the square root of 1/2. So those 2 points, and again, that makes sense because we said that our curve is going to look, something like this. So we're getting those 2 points there that are sort of symmetrical with respect to that vertical asymptote. So there's 2 points. Why don't we just throw in negative, let's throw in -2 here to get another point. That will give us 4 points. 1, 2, 3, 4. So when -2 goes in here, I get 1 over -2 plus 1 squared minus 2. -2 plus 1 is -1. -1 squared is 1. 1 over 1 is 1 minus 1 is 0. So -2, I didn't do something right. What didn't I do right? -2 in for, oh, that's what I didn't do right. See? So the reason I knew I didn't do something right was because I was getting a 0, and I've already found my 0 over here, so I knew -2 couldn't be a 0. So I just did -1 instead of -2. So that was my bad, but I caught my careless mistake. 1 over -2 plus 1. So again, this is just going to be 1 minus 2. So this is all going to be -1. So -2, -2, -1, -2, -1. So yes, this confirms that my graph is going to look something like this, which is exactly what the parent function here would have looked like, except that we've shifted everything down 2 and left 1. That is number 4 there. Find the location of any vertical, horizontal asymptotes. All right, I'm just going to do a couple of these. So remember, vertical asymptotes, we set the denominator equal to 0 and solve for x. Horizontal asymptotes, we're going to use the rules. And the rules are that we compare the numerator degree to the denominator degree. If the numerator degree is less than the denominator degree, the horizontal asymptote will be at y equals 0, which is the x-axis. If the numerator degree is greater than the denominator degree, there is no horizontal asymptote. And if the degrees are equal, then what we do is we know that the horizontal asymptote will be at y equals the ratio of the leading coefficients, a over b. Those are the rules. You really should just memorize those. You should also understand why those work out that way, but definitely make sure they're memorized. So for instance, in 4.4 function f here, so for the vertical asymptotes, we set the denominator equal to 0. We solve for x. There's our vertical asymptote. This function will have a vertical asymptote at x equals 2. So you will see this function doing, something like that or something like that. And that line where the two halves of the graph sort of are separated from each other, that will be at x equals 2. In example h, or function h, always remember that first thing that you have to do to find your vertical asymptotes before you actually figure out what makes the denominator equal to 0, if you have a quadratic trinomial like this, or really any polynomial that can be factored, you always want to factor first. So that denominator is going to factor into x plus 4x plus 2. Foil that back through, x squared, 2x, 4x gives us the 6x, and the 4 times the 2 gives us the 8. So now we can see that either x plus 4, so here, let's set that denominator equal to 0. So either x plus 4 would have to be equal to 0, or x plus 2 would have to be equal to 0. So x would have to be equal to -4 or -2. So our vertical asymptotes will be at, did we do the horizontal asymptote for this one? I'll go back there in a second. The vertical asymptotes would be at x equals -4 and x equals -2. Horizontal asymptotes here, note that the numerator degree is greater than the denominator degree, which means we have no horizontal asymptote by the rules that we just mentioned. Back up here, we have a numerator degree of 1. We have a denominator degree of 1, which means that the numerator and denominator, there's a 1, the numerator and denominator degrees are equal here, which means our horizontal asymptote will be at y equals the ratio of the leading coefficients. That's 1 over 1, which equals 1. There will be a horizontal asymptote at y equals 1 in this case. Let's do Let's do one more of these. Let's do the g function. So that's 3x over. Remember, we want to factor that denominator. That is a difference of squares. So x minus 4, x plus 4. So now it should be very clear that the vertical asymptotes, if this denominator equals 0, the values of x that will make that denominator equal to 0 are x equals 4 and x equals negative 4. 4 minus 4 is 0. Negative 4 plus 4 is 0. So our vertical asymptotes will be at 4 and negative 4. In terms of the numerator and denominator degrees here for our horizontal asymptotes, our numerator degree is less than our denominator degree. Numerator is a degree of 1, denominator is a degree of 2, which means our horizontal asymptote is at y equals 0, which again is the x-axis. There we go. Use the graph of the rational function. This is 4.5 here. Use the graph to find, we need the domain of the function, okay? So remember that horizontal asymptotes are prohibited x values. So we have a prohibited x value at x equals negative 1. We have a prohibited x value at x equals 1. So these are the two values that have to be excluded from the domain. So if we're writing this domain in interval notation, we're coming up from x values of negative infinity. We have to stop when we get to negative 1. We can continue again right on the other side of negative 1 until we get up to 1, and then we can continue right on the other side of 1 and go all the way up to, sorry, that should be a parentheses, and go all the way up to infinity. So there are no brackets, no hard brackets here. So again, from negative infinity up to negative 1, we have to hop over negative 1 until we get to 1. We have to hop over 1 to get to infinity. And again, that's because those vertical asymptotes are occurring at negative 1 and 1. Those are the restricted values from the domain. X cannot equal negative 1 and x cannot equal 1 in this function. These are the values. We don't have the function here, but we would know that these are the values that would make the denominator equal 0. The range of the function here, you got to be a little bit careful. Some students will see this horizontal asymptote at negative 1 and they'll think that the range of the function doesn't equal negative 1, but horizontal asymptotes are different from vertical asymptotes in that functions actually can cross their horizontal asymptotes. Horizontal asymptotes are just about what happens as x gets really big or x gets really small, but horizontal asymptotes don't necessarily tell us much about what's happening in the middle of a graph, like by the origin of a graph. So we actually can see that this function does go through its horizontal asymptote. There is a point on this function right here where the y value is negative 1. So while it might be true that this leg of the graph gets very close to negative 1 but never touches it, and this leg of the graph gets very close to negative 1 but never touches it, there is a leg of the graph here in the middle that crosses that horizontal asymptote, and therefore there is a point on this graph where x equals negative 1, which means the domain, the range of this function is negative infinity up to infinity. All y values are accounted for on this graph. We're going down to infinity here, we're going up to infinity here, and all the points in between cover all the y values in between. In fact, this leg here, you can see this leg in the middle, almost looks like a cubic function flipped here. This leg in the middle covers all of the values, all the y values. So the range is negative infinity to infinity. The intercepts look like, let's see here, it looks like we've got two x-intercepts, one there. So x-intercepts looks like, I don't know, let's call it negative 0.5 comma 0. And what does that look like? Is that 2? No, it's not 2. It's a little bit more than 2. I don't know. Let's call it 2.2 comma 0 approximately. So there's our x-intercepts, 1 and 2 of them. And then our y-intercept, it looks pretty clear that that's going to be at 0 comma negative 1. 0, negative 1. Horizontal asymptotes, we already talked about this. Definitely looks like there's a horizontal asymptote there at y equals negative 1. Again, the graph does cross the horizontal asymptote here in the middle, but as x gets very, very big, as x goes off to infinity, it looks like y is getting very, very close to that negative 1 value, and as x goes off to negative infinity, same thing, y is getting very, very close to that horizontal y equals negative 1 line, and then the vertical asymptotes we've already discussed will occur at x equals negative 1 and x equals 1. And then finally, oh my goodness, the fate method. What is fate? We need to factor. We need to identify the asymptotes. We need to identify the intercepts. And then we need to do a table of values. We kind of did this on a previous example or two. So what does that mean here? That means, I'll try to do this as neatly as possible. It means we first need to factor the denominator, so let's do that. This is going to be what? 2 x's, and then we need probably 1, 3, and 1, 4, 1 positive, 1 negative. It's going to be a negative 3 and a positive 4. Oops, that's not a 4. That's a 2. Let's factor this back, FOIL this back through. X squared plus 4x minus 3x. Yes, that's going to give us that plus x in the middle. Minus 3 plus 4, multiplying them gives us the negative 12. So everything checks out. So we have factored the denominator. Let's locate our asymptotes. So this is the factor step. This is the asymptote step. So asymptotes. So let's do vertical asymptotes. Remember, that's any x value that makes the denominator equal to 0. In this case, so x minus 3 times x plus 4. In order to make that all equal to 0, x would have to equal 3, or x would have to equal negative 4. Why don't we just go ahead and plot those right now? So there's x equals 3, and x equals negative 4. So there's our vertical asymptotes. It's not very straight, but that's okay. Horizontal asymptotes, let's use our rules. We have a degree of 1 in the numerator. We have a degree of 2 in the denominator. That numerator degree is less than that denominator degree. By our horizontal asymptote rules, we know that we're going to have a horizontal asymptote at y equals 0, which again is the x-axis. So that means our horizontal asymptote is the x-axis. So now we've broken this function down into some sections, sort of 6 sections here, or 3 sections, whatever you want to call it. 1 there, 1 there, 1 there. So most likely this graph is going to end up looking like something we've seen before, like maybe something like that, or like this. Usually that's what happens in these cases. So those are our asymptotes. Our intercepts, remember, to find the x-intercept, we make y equal to 0. To find the y-intercept, we make x equal to 0. X equals 0. X-intercept is y equals 0. Let's do the y-intercept first. That one's almost always easier. So that means that, so let me write y equals, I'm just substituting y for r of x. Y equals 0 minus 1 over 0 plus 0 minus 12. In case it's not clear what I'm doing there, I'm simply throwing in 0 for my x terms. That's all I'm doing, substituting 0 for x. I am getting, what is this? This is negative 1 over negative 12, which is 1/12. It's a little ugly, but whatever. So when x equals 0, y equals 1/12. So there's 1 point. X equals 0, y equals, that's going to be about right there. It's almost at the origin. So that's my y-intercept. So for my x-intercept, what do we got here? Oh, this is going to be fairly easy too. So I'm throwing in 0 for r of x, which is the same as y. So I'm throwing in 0. When I cross multiply here, let's just do 0 over 1 there. So that times that times that, I just get all this, x squared plus x minus 12 is times 0 is just 0. And then 1 times x minus 1 is x minus 1 plus 1 plus 1. And I'm seeing here that my x value when y equals 0 is 1. So 1 comma 0, x is 1 when y is 0. 1 comma 0, 1 comma 0 is my x-intercept. So again, this probably is going to be one of those situations where we're coming down and sort of bending here, something like that. We'll see in a moment. So that is our x-intercept and our y-intercept. Now for our table of values. So let's do x, y, but remember y is the same as r of x in this case. So why don't we put our intercepts in there, 1 and 0, 0 and 1/2. And now what we'll do is we will start throwing in some values. We'll throw in a couple values in this middle section. We'll throw in a couple values in this left section, and then in this right section to sort of see what's happening here. So let's use Let's use 4. Let's try that. Now listen, if you get to use a calculator, you know what? I am going to use a calculator here because this video is already very long and I don't want it to take that much longer. So here's what I'm going to do. I am going to, trying to think of how I can do this that you would also be able to do it. You know what? I'm just going to punch it in the way we normally would. But I'm going to use the store function. If you know how to do this on the TI Inspire, great. If not, no big deal. By the way, there is a chance that your teacher might literally make you do all of the arithmetic out here. So x squared, so that's 4 squared plus 4 minus 12. 4 squared plus 4 minus 12. So your teacher may make you do all of this work out by hand. But here's how I'm going to do it. I'm going to make a table here. So let me do alpha f equal. So some of this stuff you may not know how to do in your calculator, but again, I gotta make this go a little bit faster here. So x squared plus x minus 12. So what I'm going to do is I am going to go up here into my table. I'm going to throw in 4 and I get 3/8. So when 4 goes in here, I get 3/8, which is exactly what all this arithmetic would come out to. So that's 4 comma 3/8. 3/8 is a little less than a half, so that point's going to be there. Let me also now do let me do 10. So 10 and then 9/98. 9/98 is like 1/10. So that's like here. So I can see now again that based on what I know about parent functions and what I know about some other functions we've graphed that look like this, I can see that that leg's probably going to be here. I could confirm this by throwing in like 3.1 and I'll probably get a little bit of a bigger value. And indeed I do. 210/71 is about 3. So at 3.1, I'm up here at 3. So indeed I can see that my leg is going to be, this leg of the graph is going to be going up like that. Let me try a -3. So when I get -3, I get 2/3. So -3, 2/3 is here. So again, that kind of confirms what I was thinking before, that we're probably doing something like this here. In fact, let me throw in a 2.5 and see if I get a big negative number. 2.5. I don't get a big negative number, but I do get a negative number. -6/13 is about -1/2. So maybe this leg just comes over here a little bit more. I could even do something very, very close to 3, like 2.99999, and then I bet I'm going to get a huge negative number. Yes, I do. -28,000. So indeed, that's what's going on in the middle there. And then let me try a couple over here on the left. Let me try -8. And indeed, I get a very small negative number. So this leg's going to be down over here. So -8 is -9/44. That's like -1/10. Let me try something very close to -4, but on the left-hand side of it. So I'll do -4.3, and I'm assuming I'm going to get a big negative number there. Yeah, pretty big. That's like 2 point something. So -4.3, and so that guy's down there, which means this leg is probably looking like that, although it might be a little bit sharper curve there. So there we go. So my graph is going to look roughly like that. One there, one coming down there, and then one up there, with my horizontal asymptote at x equals 0 and my vertical asymptotes at, I have y equals 0, horizontal asymptote, and then my vertical asymptotes at x equals -4 and x equals 3. If your teacher does not allow you to use a calculator, obviously you're going to have to use nicer whole or integer values, but I trust that she'll give you a way to make these calculations easier on yourself, because these numbers do get quite ugly. That is it for that handout. I know it was a long video, but hopefully that thoroughness should help you understand how to do some of this stuff. Obviously, you need to do some of these examples or similar examples on your own and do a bunch of them so that you get very, very familiar and comfortable with this stuff before your test or quiz.